Good morning, everybody. My name is Koushik Sinha, and I'm from Southern Illinois University, Carbondale, and today my talk is going to be on dynamic spectrum management for multi-rad-based multimedia data communication. So this is the topic that we'd like to, uh, you know, use for conducting some experimentations on the Cosmos testbed, and we're really excited about the potential about it. So just to give you the motivation as to why we chose this particular topic for the Cosmos testbed, well, some of these statistics all of you know about. It's expected that multimedia data is going to be the major driver for internet traffic consumption in the pretty near future. And what that's going to lead to is that the aggregate bandwidth demand is going to exceed, most likely going to exceed the available licensed spectrum bands. So the only option over there is most like that we're going to be forced to use the unlicensed spectrum bands even for cellular network communications and so. And now when that starts happening, obviously because you're going to be using unlicensed spectrum bands, you have to, you need to compete with the existing operators in those bands, and that leads to the problem of increased interference coming from other users, and that would be and that problem becomes even worse as we are going to move to the 5G networks with ultra dense base station deployment. And what's that going to lead to is that we're going to see that even though we have more spectrum available, but the overall quality of the multimedia data transmissions might be adversely affected. Now, and as we can, as the most consensus is that Wi-Fi and LTE is probably going to be the dominant technologies for the foreseeable futures, right? So that's what most people have been using so far, and that's probably going to continue for quite some time into the future. As we all know, that LTE deployed in unlicensed band, it's termed as LTU, and the way LTU has been proposed is that it's going to be used for supplemental downlink, while uplink will still continue to be using the licensed spectrum band. So this is the case where the users would be downloading data in the unlicensed band, and the control and other information, or uploading of information from the user side to the cloud is going to happen using the spectrum, using the licensed spectrum band. Now, that's definitely a challenging deployment scenario, as you can understand, because since the users don't transmit in the unlicensed spectrum bands, but they will continue to experience co-channel interference from other Wi-Fi transmissions that are in the vicinity. And with 5G, we expect that that's going to become even worse, because 5G proposes to use direct device-to-device communication. And for example, you have LTE Direct and Wi-Fi Direct, which have already been proposed. And when they go online, so what's going to happen is that you're not only going to have interference from Wi-Fi communication, but you're also going to be experiencing interference coming in from direct D2D communication, which could either be ad hoc or controlled by the network operator itself, right? So essentially, dynamic spectrum management, therefore, has become quite an hot area of research right now, and which is why that's what we intend to focus on, particularly given that there is a lack of interoperability between these various radio access technologies that's out there, and that's going to come up in the future. So our overall goal, as I said, is that we want to design a dynamic spectrum management system, a unified spectrum management system for a multi-rad based multimedia data communication scenario. And to achieve that, so we realized that this is not going to be a one-shot job, and there are multiple steps that needs to be done. So we thought that, okay, we'll start off with a modest, simple pilot, and then gradually ramp it up in multiple phases. So in the first phase, what we intend to do is that we intend to just deploy multiple user equipments, which should be just for downloading multimedia data. Okay. And what we really want to do, and that we want it to be a mix of stationary and mobile UAs, right? And what our goal over there is essentially we just want to collect some statistics in terms of what sort of multimedia data people request, and measure quality of experience parameters like the link throughput, the latency, jitter, overall packet loss, and all of these, whatever information that we can actually gather regarding multimedia links that the mobile and the stationary users would be using for downloading data. And simultaneously, we would also like to gather some statistics on the spectrum usage map, essentially in terms of allocated bandwidth per link, channel statistics, and what part of the spectrum is being used, and so on and so forth. Whatever information that we can gather. So the idea is that with those information, we would be able to formulate our algorithms, or fine-tune the algorithms that we have developed and which we intend to implement in our phase 2 and phase 3 part of it. And the third thing that we really want to do is that we also want to evaluate a simple interference characterization model that we have developed that essentially provides a unified view, unified model for determining what sort of interference can be experienced in the presence of Wi-Fi, LTU, and LT direct, Wi-Fi direct type of communications that would exist. So that's what I talked about. And for this part, we would assume that we'd like a deployment scenario consisting of, say, N Wi-Fi, M LTU, and some Q D2D. So essentially a mix of Wi-Fi, LTU, and D2D communication links, and make the standard assumptions in terms of Wi-Fi and LTE setup. And our goal essentially is to validate our proposed interference characterization model, which is a SINR of a Wi-Fi link in the presence or absence of LT and D2D. Similarly, for LT in the presence or absence of Wi-Fi, and for LT direct in the presence or absence of Wi-Fi and LTE. So that's the first phase that we would like to do. So once we have completed the phase 1, so that's when we would like to move on to phase 2, which is essentially the meat of our work, which is going to be a global spectrum allocator design that we have been working on, and what we would like to implement on the Cosmos testbed and evaluate its performance. So what this global spectrum allocator, the GSA as we call it, is what it's going to do is that our goal is dynamic channel allocation to handle demand simultaneously from LTU, Wi-Fi, and D2D, with the goal of minimizing the total allocated bandwidth while avoiding co-channel interference. Okay, and our aim is to design GSA using SDN architecture features so that it's scalable and it can actually work on top of all of these different multi-rat scenarios that we will have in the future as well as we have now. We do also consider the presence of both in terms of D2D communication, which is the particularly challenging part of it, because if you think about Wi-Fi and LTE, well, that's kind of like not so difficult because both of them are kind of like centralized. You have base station or access point from where you can collect the information and kind of figure out how to do a spectrum allocation. But the moment you introduce the D2D communication, that becomes much more challenging because these D2D links could either be all within one cell, or a particular D2D link could actually span multiple cells, right? It could probably span 2 consecutive cells. So then the question is, how do I do the spectrum allocation so that I avoid channel interference and at the same time trying to minimize my overall bandwidth that I'm going to be allocating to that? So that becomes a really challenging scenario, and we've kind of developed, and we have actually come up with several papers on that. And our idea is actually to go in and implement those ideas to see how they work in real life base station deployment scenarios, where obviously there are certain assumptions that we make for channel allocation, like regularized shape of the base station, the cells and all those things don't hold good anymore, right? So then there is the question of how do they perform in the presence of actual deployment scenario. So first goal is to evaluate the performance of the current centralized GSA that we have developed. So essentially we want to implement and evaluate that, and the next step would be what we are working on currently is to come up with a distributed or a hierarchical GSA, and that's what we would like to implement and then evaluate the performance of that too, right? So that's our phase 2. Phase 3 is actually closely connected with phase 2, and what this is trying to do is that in this what we call the multimedia sub-packet generator, The idea over here is trying to address one, a major or critical issue that we face, which is the inability to transmit multimedia signal because of fragmentation of the available spectrum. Like, for example, if you see over here, if a particular link requires, a bandwidth equivalent to 4 channels, even though I have more than that, but because the spectrum is fragmented, I won't be able to allocate that. And it's a classic case of, memory fragmentation, right? So can we still allocate channel without having to move users around and then do it? So what we have come up with is essentially a new concept called sample division multiplexing. And what it does is that it does a non-contiguous channel allocation to satisfy multimedia demand. So what the MSG unit is going to do is that the idea is that the MSG unit is going to provide the number of channels required to satisfy the bandwidth requirements for the multimedia signal that has been requested. Okay? Now, using that information, the GSA would fine-tune its allocation strategy. So the two possible implementations that we've been looking at, so the MSG is actually going to be sitting at the file layer interface, so we would actually need information from the file layer and also have access to the file layer. The two possible implementations that we have considered is FDM with FDMA and OFDM with FDMA. So these are the two things that we would like to implement and evaluate this performance. Now, the MSG, as you can understand, obviously this is going to happen at the network side, right? And now, what's going to happen is that the signal is going to be split up into multiple such, channels, and the data is going to be transmitted. The SDM is going to transmit data to those multiple channels, and the user equipment obviously are going to receive that and needs to, recombine that information to reconstruct the original multimedia signal that was transmitted. So that part right now we aren't really considering it because we'd first like to evaluate, right on the network side to see how well we can, fine-tune the GSA. And later on, we would definitely like to also focus on the user equipment side so that we have the complete system of using the MSG along with the GSA and then having the UV receive that and recombine it and studying the overall effect of this entire process in terms of the quality of experience parameters over there. Okay, so so overall, essentially, I don't want to really go through it. I think I've already talked about it. So essentially, as I said, is that the MSG is going to be a feedback to the global spectrum allocator, and finally, the output would be an interference-free channel allocation over there. And there's a feedback loop that's happening. The information from the users is going to come in, and that's what we're going to store in some databases, and also using the channel classification. So the global spectrum allocator gets all this information and then does channel allocation over there in that case. Okay. So so that's all from my side. And so any questions or comments? That's it. Yeah.